Hello everyone, October 5th. Alright, so today's a little bit earlier. Just finished a bit earlier. Yesterday was crazy. Alright, what's this? Majority element number 2. Given an integer array size n, find all elements that appear more than n divided by 3 times. Could you solve the problem in linear time in O1 space? More than n divided by 3. More than n divided by 3. Oh, floor. So I just find all the things that appear more than a third of the time. Well, I mean, of course, we can counter it, right? If we do a counter, problem solved. If you do a counter, problem solved. You always have it. Now, the issue is, what if we don't do counter? Because you do counter, it's O(n) space, right? Let's just solve this first. That's how we always do. Just solve it first, and then we'll handle the other things later. We can say map, right? Counter for a int n of nums, counter dot put n, counter dot get or default n 0 plus 1. Okay, once we're done, we want to return all elements that appear. So I guess it doesn't really matter on the order. So we say int, a list. Okay, list integer res equal to new array list, right? For int key of counter dot key set, right? That's fine. If counter dot get key is more than math.floor, what can I also say here? Int limit is math.floor nums.length divided by 3. Here we'll say lim. What's wrong with this one? Double. Hold on, it's not. Provided double require, hold on, floor. Yeah, floor is double. And no way, it returns it turns a double. Huh. I mean, we do this is already integer division. Integer division is already flooring, so I think it should be fine. We'll just do that. We say if that res.append, now add k, right? And then we'll return res. Okay, just give it a shot. Are we good? Are we good? Should be fine. Pretty straightforward. Alright, I've done this before, but never really. I was trying. 2 years ago, trying hard to do it O1. So what do you think? Right? What do you think is the ideal of O1? I honestly have no idea. This is O(n) space and on time.
Hey.
Ugh. Okay. All right. Now we need to figure out O1. How would you do this for O1? It's a good question. O1. O1. How would you do it for O1? O1 space. So just basically we do it inside, right? You have 3, 2, 3. I'll do it inside to know if it's any value. It's appear more than a third of the time. A third of the time. Right? It's more than a third of the time. What's so special about a third? Well, I mean, you do this, so more than one time. So you have a target, right? Target, you have a target. So this target is 1, so it should be larger than 1. So in the find, just basically given an array of numbers and tell me which one is. But I feel otherwise I can do anything. And more than a third has to mean something, right? It has to mean something. It has to mean something. Well, if more than a third, so maybe, I don't know, can we say, if we have an array, right, if we divide it into 3, so there's 1, 2, 3, 4, 5, 6, 7, 8, right, 8 divided by 3 is 2. Floor is 2, which means we can do this plus 1, it's 3, so at least it has to be larger or equal to 3. So we can set this, okay? And then what? Then we have, let's say, I, J, and K. Well, it's not gonna be K because it's only gonna be I and J, right? Because at the end it's not gonna be larger than 3. It's just gonna be I and J. So as we go through this thing, every time we hit a value 3, we put in here, right? And then we move this one forward. Now we make a 2, so we put in here, we move J forward, all right? Next one 3 again, but how do we know the previous one is 3? And what if we hit another one? We can sort it, right? Sort is O1 log n. It's not linear time, but it's O1 space. Well, I mean, more than a third time. So it should only be 2, right? Yeah, it should only be two values. There should only be two values. Wait, would it be like like nothing? I bet, like if we do this, right, and then it's nothing. The last one should be empty. It should be empty. So because it's larger than a third, and the larger than a third, so at most is two values, right? So at most is two values. So we just need to find two values because it cannot be three. Because if three values, each one is larger than a third, then it will be larger than n. So that's not going to happen. Not be possible. So, in other words, what we need to find is the largest, most occurring, and the second most frequent. That's what we need to find. So now we convert the problem to finding the most frequent value and the second most frequent value. How would you find that? The most frequent value. Yeah, I just say the most frequent value. How would you find out who is the most frequent value? By going just O(n) with O1 space. Most frequent value. Oh yeah, you just no. What? Oh yeah, you can't do that. You have to keep a record, right? You have to keep a record of them. The most frequent. So you met somebody, and you do it again. You met somebody, and then you met somebody again. How do you know this one has been encountered before? Right? How do you know? You don't know, right? You don't know. Well, you're going to return two values, right? Or one value. 2, 1, or nothing. Okay? So what if you go through, let's say, the first value you encounter? You try that. Okay? You count how many it is. And you go the second value. You try to count how many it is. No, it doesn't sound right. It does not sound right. Does not sound right. Let me think again. What else can you do? Can we, let's say, like do the pivot thing? Like larger than and a smaller than? Would that help? Well, if we do the pivot thing, let's say we just set the first value, right? And we say anything larger than that can go to the right side, smaller or equal to, and smaller than that go to the left side. Okay, so we're trying to pivot. Okay, so some value here, right? And then we do an I and j. And now we say j, if it's larger than, we move forward. If it's smaller than, yeah, what about equal? Let's just say smaller than, then we all swap. Okay, then this will move forward. And then it'll swap. So at the end, we'll have smaller than, so this is smaller than, eventually I and j will meet each other, right? I and j will meet each other. J will move if it's larger than, then we move, right? If it's smaller than, I will swap. If it's smaller than, I will swap. Smaller than, or if it's larger than, then we'll move forward. So eventually, when they meet each other, it will be something that's smaller than. Well, it's either smaller than or it could be anything. But anyway, so we know these, because these are what we swapped there. So these are smaller. These are larger equal to. Right? Yeah, if it's big, I go. If it's small, or it's equal, I also go. But if it's big, I go. If it's small, then I swap. If it's small, I swap again. Small, I swap again. And then I will end up, they'll be small, right? So if it's, I swap, it's big. And I go down, yeah, so it's gonna be small. Right, so this will end at a small. Okay, these are small. These are smaller, larger, equal to. So I can swap this and this. We do one more swap. Then we have the first half, it's smaller. And then we have our target. And then we have this half is larger, equal to. Then what? Well, how does it help? So if you are more than a third, more than a third, I have no idea. Do you have any hints? How many majority elements could it possibly have? Two, I said. Two. You can only have two. So yeah, it is. Okay. So, I mean, we realize that, but I just don't know how to use it. We have two, right? The largest and the second largest. And of course, if the largest is smaller, then that's just done. If the largest, so yeah, the question: how do we find the most frequent? Right? Is there an algorithm to find the most frequent in O1 space? O1 space. Like, how do you even find it in O1 space? Yeah, I just have lots of values in it. Yeah, one majority. But how do we find out which one has the majority? Well, majority means more than half. Alright? If one is more than half, it's a third, right? More than a third. And the other one is more than a third, then we can, yeah, then we can add more, right? We can add more. No idea. Boyer-Moore voting algorithm. I forgot about this completely. What the hell is Boyer-Moore? Oh, okay. Boyer-Moore voting algorithm. Yes, we get this. Okay, 2. How do you keep track of a majority elements? One holding a potential candidate for majority element and a counter to keep track of whether to swap a potential element or not. Why can we get away with only 2 variables? Because there can be at most one majority element which is more than this. Having only one variable to hold the only potential and one counter is enough. Why? While scanning the array, the counter is incremented if you encounter an element which is exactly the same as the potential candidate but decremented otherwise. Ooh, decremented otherwise. When the counter reaches 0, the element which will be encountered next will become the potential candidate. Keep doing this procedure while scanning the array. However, when you have exhausted the array, you have to make sure that the element recorded in the potential candidate variable is the majority element by checking whether it occurs more than this times. In the original problem, it's guaranteed that there is a majority element. So implementation can omit the second pass. However, in the general case, you need a second pass since your array can have no majority element at all. The counter is initialized as 0. So hold on. So let me summarize this. So you pick something, right? You pick some number and then you say, okay, let's just say this one is a majority. And then we did pick it and then we're done, right? If it is not the majority, then as we go encounter something else, you will decrement it, right? It will be decremented. And then it will be decremented 0, right? Because it's not like if there exists a majority, then it is guaranteed that whoever its initial you're getting at, when you hit the majority, right? When you hit the majority, so whenever I encounter this, right? And when you hit the majority, and you're saying that the remaining value, among the remaining value, the majority is always going to be more than half. I mean, if you start from the beginning, you can say, okay, the majority is more than half, so eventually the majority will win out, right? Majority will win. Okay, I agree with that. But if you already consume some of the majority, right? It seems right. It seems right, but is it a proof for this? Yeah, it seems right. We have a majority, right? We have someone that's just more than half, which means if there's another one, we only have one other, then it will always work. If we have two others, right? I have two others, but one is majority, so two others, those two added together is not more than what we have. So it doesn't really matter whichever one is counted, right? It doesn't matter whichever one is counted. Eventually, the majority one will win out. Yes. Holy sh! It does make sense. It doesn't really matter which one you count. The majority one will win out because every time you hit a different one, you just decrement, right? Every time you hit it, you increment. You hit another one, decrement. So eventually, it's just the number of times, right, you will hit the majority will always be larger than the number of times you will hit the non-majority. So even if you're always hitting the non-majority, then eventually you will land on the majority. Wow. Boyer-Moore voting algorithm. Okay, so that's for 2, right? And then for 3, I would imagine, because for 2 you need one candidate and a one counter for the candidate. Now for 2 majority values, so you need 2, right? You have candidate 1, candidate 2, count 1, count 2. Then how will we do? So again, if you hit the candidate 1, you increment. You hit the candidate 2, you decrement. And when you hit someone that's not candidate 1 nor candidate 2, then what do you do? Who do you decrement? Do you decrement? Well, if there's only one majority, not majority, one more than a third, right? Then you hit it, you increment, 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 increment. And then if you don't hit it, you decrement. Or do you decrement on both? Because eventually you want the same kind of idea, right? You want the same kind of idea that if we hit a none, then we hit a real one, your decrement. You hit a real one, then you're a decrement. So if you're in a wrong position, you always get back to negative, right? It will always get back to zero, right? You will always get back to zero. But you just have two, right? Two things. So you hit one, you decrement to zero. Yeah, because these two are, like I said, the candidate, right? These are the candidates. And if we just hit, candidate, hit, and then we hit this, then we add another candidate, another candidate, and then we hit another one. So 2 is already being set. Then we hit another one, then this one to decrement. This one is a decrement as well, right? So this one decrement, this one decrement. Then we hit another one, this one decrement, this one decrement. So eventually one of them will become 0 first. So whenever it becomes 0, I swap in. And now we hit another one if it's different, then it will. So yeah, so it's 2 counters and 2 candidates, right? And then we can initialize the counter to -1, so you never know which one has been set. So you go through this. Here's the first one, you try the first candidate to see if it have not, you just do that. And then the next one, you try the first candidate, it's set. Then you try the second candidate, if it's not set, you do that. If it both are set, then you decrement on both, okay? You decrement on both. Yeah, you decrement on both, because eventually what we want is, if it's not, it needs to decrement to 0, so you decrement on both. And then another one, if it's not the first one, you decrement on first one. If it's not the second one, you decrement on second one, right? If it's not first one, and then if it is, then you just, yeah, so I think it still counts as just a hint because I'm not reading the actual solution. I'm trying to solve this without going through the actual solution. Boyer Moore. Okay, so this is from the official solution. Boyer Moore algorithm. We want to find the top 2 majority elements in nums, right? We set up 2 candidates and 2 corresponding counts. If a third element is encountered, both counts decrement. If any count decrements to 0, we swap it out. We swap the candidate with the current value. Right. Eventually, we will end up with 2 candidates that potentially have more than a third count. or we should say eventually we'll end up with two candidates. Now, if any element indeed has more than 1/3 count, it will be one of the two eventual candidates. However, it is also possible that we do not have an element with more than 1/3 count. Therefore, we have to count the candidates again just to make sure. Yeah, so this is, we can just say this is O n time and O1 space. Alright, so here's the thing. Int, right, cant1 int cant2 int count1. Okay, ca1 candidate, ca2 co1 equal to 0, count 2 equal to 0. Yeah, so cnt candidate cad. Okay, so cat1 cat2. Okay, so for int n nums, right? If count1 is 0, right? If count1 is 0, then we say cat1 equal to n, count1 plus plus. Else if count2 is 0, okay, then cat2 equal to n, count2 plus plus. All right. Else if, so neither is 0, so cat1 is equal to n, then count1 plus plus. Now it will be initialized, so yeah, but we can just do doesn't matter, we know it will be initialized. But anyway, else if cat2 is equal to n, then it will increment. Else, so now this is neither, right? Then we say count1 minus minus, count2 minus minus. Now here is important, right? Here is important. Huh. I just realized I probably should do it some other way. What if we do this one first? Do this, this, and this first, right? And once we're done, then we check. You see what I mean? Here's kind of the idea. So we'll do this check first. Makes sense, right? So we'll start with, let's say, math.integer infinity max value. Okay, integer.max value. So we start with that. Okay, we say if it's equal to n, we do this. If it's equal to that, then we do this. Else, if it's both not equal, then we will minus minus, right? Both will minus. And then we'll check. If it's, then we do this, right? If this, we do this. If nothing, we don't do anything. Now with that, we are ensuring that the start, yeah, because it's max value, so start with 1. And I want to come in, the first one will be false, false. So it will do this. Once it's done, both become 0, so we check this. Next one coming in. If it's this, then good. If it's this, if it doesn't equal, right, then we'll minus minus. Oh, but hold a second. This one will give minus minus, but it doesn't change, right? What if both become 0? What if both become 0? I guess. If both become 0. Yeah, that's fine. If both become 0, we'll always do count 1 first, right? And if the next time we come in and then count 1 is not equal to 0 but count 2, then we'll handle count 2. But it doesn't matter. We just go through the whole thing, right? And then what we do know, right? What we do know is after we get out, we have 2 candidates, right? Then we just need to check the count, right? The count. Then we say count 1 for the 0, and then for int n nums. If n is equal to candidate 1, count 1 plus plus. Right, so we say count 2 is also equal to 0. If n is equal to cat 2, count 2 is plus plus. And at the end, say int limit is equal to nums.length divided by 3, right? Then we say list integer res equal to new array list. If count 1 larger than limit, res.add cad1. If count 2 is larger than limit, then res.add cad2. Then I return res. Okay. What do you think? Oh, I missed 1 and 2. That's funny. So this one, 1 and 2. Well, 1 and 2 will come in 1. It's not equal. Right, so it will be minus minus. Then it's 0, so cat 1 is 1. Cat 1 is 1. And then 2 comes in, not equal. This is minus minus, this is minus minus. So both become 0 again. And the cat 1 is 0, so I get to become 2. Interesting. So maybe that's not the way to go. Maybe. Okay, so then what? Well, I shall. Yeah, because candidate 1 and candidate 2 has to be different, right? Which means if I have something open, I should not replace candidate 1. Yeah, I shouldn't replace. So the condition needs to change a little bit. Need to change. So if it is, then we definitely check this. If it is, then definitely check this. If it's not, then we go through this part. So what if I set both to 0? But you don't know which one has not been initialized first. So I need to initialize them. Yeah, I think I'll just do here. I'll say if cat1 is equal to integer max value. All right, no question. Else if cat2 is equal to integer, then we'll do that. Else if count1, so we handle those first. Right, and then we handle this. Yeah, it's different. You can't just put these things together. It has to be different. These take precedence. And then else if count2 is equal to 0. Then cat2 equal to n. So with this change, okay, let's try this one. What the hell? 3 and 3. So they has to be different. And cat2 is not equal to cat1. Okay. Try that. Ugh. So 2213. So 2213 comes in. Okay, so cat1. I have next to again, it's equal. I think I need to continue. If we find it's equal, then we should continue. Because that just end. It still doesn't work, huh? Yeah, it isn't. It's not right. Well, what we can do is say if it's smaller equal to 0. If it's smaller equal to 0, right? Then we set it to 1. Set it to 1. What the hell? It's still not right. Yeah, because I think 2 we get it, right? And then, okay, so this is the same. So we should set it to 1. Boop, 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 boop. Now we set this to 0. Boop, 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 boop. Doesn't work. Alright, I need help. Simple, we just do this 2, 2, 1, 3. Majority element. Yeah, I just put it here. Okay, enter. No, F8. No, no. So we have -1. Yes. Okay, candidate 1 is 2. That's good. Candidate 2. That's good. No, no decrement. Okay, so right now n is equal to 1. Candidate 1 is 2, so this is false. This is true. Okay, so candidate 2. And then we're gonna go no, no decrement. Candidate 1, no, no. Candidate count 1 equal to 0. How is count 1 equal to 0? Hold a second. Doesn't make any sense. 1 round, 2 round. Count 1 is 2, right? Count 1 is 2. And then we hit... Oh, shoot, it is. It is. So the first one, but if it can fit into a different one, we shouldn't decrement it. All right, that's the whole idea. because we have another box. If we have two boxes, we can hold stuff. So we shouldn't decrement. So here is, this is why it's wrong. Okay, these two are right. Okay. Now we know they're not the same. Okay. Then we say if it's equal to that, right? If it's equal to that, or we can say if it equals to that, then we set it. If it equals to that, then we set it. So now they're not equal to any one of them. Okay. Then what? Then we need to check. Yeah, we need to check if there's any position that we can fit. Right? If there's a position we can fit, which just basically mean if it's something, if something is 0, that means that is something we can fit in. Which means if, I think I can just go ahead and say if count 1 is equal to 0, then we just do that. Right, and then we say if count 2 is 0, right? If count 2 is 0, anyone is 0, I do that. If no one is 0, I think what I shall do is if count 1 is not equal to 0 and count 2 is not equal to 0, if neither is equal to 0, right? If neither is 0, so both have been occupied, then we decrement. Right? If both are occupied, we decrement, and then we check. Now, if anyone is 0, that means we can fit in there, so we don't do that. So we'll do something like this. And if we do something like this, and if we run, now we get it, right? Okay, let's try one more time. It's on you. Ugh. That's all right. I just need to figure it out. All right, why is this one all right? So we get 2. Okay. Next one we shall get 1. Okay. Next one is 1. Next one is 3. So we'll decrement both. Okay. And then we'll replace the first one. So it's 3, 1. Okay. Next one is 1. Okay. Then 4, 5, 6. 4, 5, 6. Then 1 gets decremented, 4 gets decremented. So 4 are decrement, so because count is only 2, right? So 4 will decrement. Five will decrement. 6 with decrement. So I can't decrement both. They're different. So the other majority should not use the decrement. What do you mean? So we have 3, right? And the rest, if each one we do a decrement, it'll get the negative, right? It'll exhaust it. So then what do we say? So the idea is a third. So you're selling? Are you saying that when we decrement even it out, like a half? When we increment by that. When we decrement by half. Decrement by half. That is interesting. So you're saying we start both as float. Right? And then we do minus equal to 1.5. Are you sure? Or with plus equal to 2. Right? If we each time we count with plus equal to 2, and when we decrement 1 on both sides. So if we do that, do we get a good result? That is very interesting. I'm not sure if it's right, but I think it's worth a shot. But I have to check off if all the other ones correct. Notice that when CAD1 or CAD2 matches current element, we increment by 2. Right. This is to accommodate the decrement. Right. Since for each mismatch we decrement 1 on both counts. In other words, a mismatched element is counted twice. Hence, each matched element must count twice as well. Okay. Does this work? Yes, that's the trick. This is the trick. All right, now I can check the previous solution, or let me just check this. Okay, what's the official solution on this? That's just plus plus. Use integer. Cool. So if it's not null, and then switch plus plus. Not null plus plus. If this plus plus, if this plus plus, else minus 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 minus. How'd you handle the things that I had a problem with? If it's not null, and it's equal to, then what's this null in? Because this is equal to n, and that means candidate 1 is not null. Really? What the hell? Oh, no pointer. Oh, yeah, I cannot do. No, we can. I can use my trick. Right? Well, I'm missing again. So, I understand that. And then I say else, which means it doesn't equal to anyone. Then we check. Whoever is available, I'll set it. And whoever is available, I'll set it. If nobody is available, I'll do minus minus. So I think the difference is if you have someone, so I will set it. Whenever it becomes 0, I'll set the current one. But what this says is whenever it's 0, you leave it be. You go for the next round. That's the big difference. That is the big difference. Oh, when the counter reaches 0, the element which will be encountered next. Yeah, that's why it's wrong, this one, because I'm basically reusing the element. the element shall already annihilate with whatever is in the counter, right? And you should not use it again. Oh. Yeah, it will stick in the potential candidate value. But the true majority will definitely remain. Wow. Good. Was good. Right? How do I rate it? I want to rate it too. Alright. This is the official solution. This is a better implementation. Boyer-Moore algorithm. Yeah. Okay. Done. Let's take a look. I mean, it's late, but I need to take a look. And last night I fell asleep while thinking about the other difficult problem. Given a function, return a curried version of that function. A curried function is a function that accepts fewer or an equal number of parameters as the original function that returns either another curried function or the same value the original function will have returned. In practical terms, you can call the original function like sum. You will call the curried like curry sum or this. All these methods of calling a curry function should return the same value as original. So curry function will pass a function, right? You will pass a function, and then so a function is this. If you do a curry sum, then you do C sum 1, then 1 gets curried, right? 1 gets curried. Then this function you call 2. Yeah, it becomes 1 plus something. Then you call this, they'll give you the result, right? Because you curry this. Oh, that's very interesting. Yep, you're just passing this, and then you'll return a new function. Okay, whichever argument you pass it in. But how? Holy crap! This is very interesting. This is very interesting. Right, you pass it a function, and somebody want to curry it. Okay, you want to curry it, and then the curried version of this function can take however many arguments. Now it depends on how many arguments that this one has. Oh, look at this! You can pass nothing. What the hell? Seriously, what the hell? I mean, I don't even know. Do I know? Okay, so given a function, that's actually a good question. That's something I need to know. So given a function, okay, let's say given a JavaScript function, number of arguments, exactly. Arguments.length, it does have. hold on, it's actually passed to. No, it's not passed to. Oh, this is kind of already curry, right? It's a function have base and then base equal number base star length. Yep. Look at that. Arguments. Arguments dot length. Okay, so now that we have this knowledge, okay, and we have this knowledge of this original function that's getting passed, do we know the number of arguments? That's actually a good. That's a good question. Maybe we can try it. You know, we can say, right? Now just foo equal to. Now let's do this. It's fine. Well, we just do this. It's okay. Then we can say console.log arguments. Right, and then when we call, we say const foo equal to ab, a plus b. Okay. Then we call curry foo. Okay, so we're going to try. We say node 2632 arguments 0 function foo. That's not what. Oh, maybe I can do if this. Now I'm no. I cannot do that. I cannot do that. I cannot do that. I don't know this functions. All I know is the outer functions arguments. I don't know the inner functions argument. Current function, right? So yeah, so that's a current function. And now I call this, basically this pass 1 into it. And I call function 1. Prototype. Wait, hold on. This is a capitalized letter. Function prototype. Dot get prototype. Say object get prototype. No, that's prototype off. Get prototype off function. Nothing. It was nothing. What? I guess it's not prototype. Undefined. Maybe I shouldn't define it this way. Maybe I should define it this way. It's not full sum. Okay. Neither has. JavaScript. Number of arguments in a defined function. Oh, look at that. That's the obscure thing. Function length. Dude, we got this. We got this. It's dot length. It's dot length. I think this is the key piece of information. This is the key. I think it shall work for this function as well. What the hell are you doing, man? Yep, my Google skill is pretty on point. All right, so now I have the length. I think this is incredibly important. Okay, incredibly important information. I have the length. So when we call this, then we know, right? Then we know arguments, right? We can just say const arguments. Curried args equal to this, right? So I'll return a curried function, right? And then what we need to do is for each argument just push into this, right? Push into this. Well, we'll return a function that a curried function. So every one will say for, you know, const a of args, const a of args. Curried arguments dot add push a. Until it gets too much. So what we call too much, yeah, I think if you call too much, it will just report error. We'll return a function, okay? And this function depends, right? We return a function, and function we can call it. So what does curried function return? Curried function shall return curried, right? We should say if dot length is equal to function dot length, right? If they're equal, then we'll return function curried arguments. Otherwise, we'll return curried. What do you think? I think it's worth a shot. I'm curious. I'm very curious. Oh, this one works. Try it. Yes. 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 The key, at least in this implementation, the key is function.length. That is the key. Okay, that is the key. No other key. So the key to solving this problem is to know that in JavaScript, a function.length is the number of arguments the function will take. See the documentation. Where? This one, right? Or is it arguments.length? Just function prototype. This is the one. Boom, boom. Now I go check this. You know what? It's late. I want to stop right here. We'll read about this tomorrow because I truly believe this is a very important concept. So I'll shut it down and I'll see you guys tomorrow. Adios.